Hey guys, today we're going to talk about logarithmic and exponential conversions. So we're going to start this new unit where we introduce a brand new function called the logarithmic function, also known as logs for short. I'm going to try to give you best of a background as possible to help you understand why we use logs, how we use them, and then how are they relevant as we're moving forward. And hopefully as we progress through these next couple of videos, things will start clicking and making sense. Of course, nothing through distance learning is going to be as good as being in the classroom, but I think you guys are doing a great job. We're condensing the material as much as possible while trying to give you the most as possible so you can move forward. But you'll definitely see a lot of this again in pre-cal and as you move on through math. So let's go ahead and get started. Now, before we actually get started, I do want to talk about how logarithmic functions, logarithms sound like algorithms, but they're not the same, right? An algorithm is spelled like this versus logarithm, right? An algorithm is when you have a set of rules or processes like that you have to follow, like they ask a question and then there's like a yes or like a no, and if you answered yes, for example, then you would follow this other system where you were being asked another set of questions, right? Kind of like a survey or like a poll or some sort of way of a computer system where you go through and you keep asking more questions, and depending on how you answer, it'll tell you something or something else, right? Of course, algorithms are being used as processes for your computers, for your cell phones, anything that's being programmed. Logarithms are a whole other separate thing. I just want to make sure that this is clear, that an algorithm is not what we're talking about here. We're talking about logarithms without the A. Logarithms versus algorithms, okay? Part of this is you got to be able to practice saying logarithm, logarithmic function, logs, things like that. And we'll get into that here as we move forward. All right, let's get started. So, what are logs or logarithms? Here is the definition of what a logarithm is. This is a connection between a logarithmic function and an exponential function. Here we have it in log form, and here we have it in exponential form. We'll talk more here in a little bit about how they're inverses of each other, but you basically take the log of a function so that you can deal with a number or a large set of numbers that are vastly different from each other, right? Like 10 and 10 billion are so opposite of each other. How do we quantify them? How do we scale them down so that we can talk about them and we can compare them so that they make sense, right? The only way to do that is by taking the log of these numbers, and it scales them down, and it allows you to talk about them as 1, 2, 3, 4, 5, something that are closer to each other versus so far apart, right? If we were to make a number line or a graph of a number that has a 10 and 10 billion in it, I mean, that graph would be enormous. So what we do is we scale everything down by taking the log of that number or that function. It scales it down into numbers that are more quantifiable, easier, and closer to each other. We'll get more into this here in a bit, but what I mean by taking the log of a number is I'm going to take the log of this right-hand side, for example, y b to the x. So here, if we take the log of the left-hand side, I'm going to take the log of the left. By doing that, it allows this base of the exponent to come back down, and it writes it as log base b of y equals x. So now we're just dealing with the x, and x is a smaller number that we can deal with versus this enormous number that we're dealing with. Here, for example, we see 10 billion, right? It's 10 to the 10th power, or 10 with 10 zeros, or 100,000, right? Where you have 100 thousands, 100,000 or 10 to the 5th power, right? How do we talk about these two numbers that are so far apart into a smaller scale? So what we do is we can convert these large numbers and bring them down into a smaller scale by using the same property that we just did right here. And I'm going to show this in multiple forms throughout the video. How do you convert a regular number to a exponential, and then from an exponential to, say, a logarithmic number, so you can convert them to smaller scales. But here I'm going to show you a small example of how I do that. I'm going to take this 100,000, or 10 to the 5th. All right, we have 100,000 is the same thing as saying 10 to the 5th power. So I'm going to take the log of 100,000, and by taking the log of the 100,000 side, I'm allowed to convert this exponent, take this and bring it down to the base. And I have log base 10 of 100,000 equals just 5. This 5 just comes straight down. So instead of saying 100,000, I can just say, how about we just talk about the number 5 when we're talking about this value, right? Why don't we just say 5 instead? And we can do the same thing with 10 billion. Why don't we just say the number 10 and we convert it, and now 5 and 10 are closer to each other. They're closer related to each other, and it's easier to say 5 versus 10, right? On a scale of 5 to 10, that's more like graspable by the mind, and definitely easier to graph when you're dealing with that kind of stuff, right? It's harder to graph two numbers that are 100,000 and 10 billion. They're so far apart, they're so different from each other, but it's definitely easier to graph something like a 5 or a 10. So as a basic introduction, we're going to be able to take these large numbers, use logarithms to convert them to a smaller size, so we can talk about them in a different form. So how are they used? Now, in high school, you're going to talk about this in chemistry. You're going to talk about the pH scale. If you haven't already, you're going to talk about perhaps earthquakes in science, or in history for sure. You talk about the history of earthquakes and how they come about. But Richter, you created this Richter scale. This is how you spell Richter. He created the Richter scale, where he was able to quantify and compare like the magnitudes and intensities of these earthquakes. So I'm going to show you a small example here so you can sort of give you an understanding of what this means. So let's say that an earthquake starts with first like an epicenter, right? And then the earth vibrates whenever there's an earthquake. And I'm not going to get too into the details, but plate tectonics comes into play. And if you know a little about tectonics and how the earthquake sort of, the earth shifts, and as it's shifting, it's creating this vibration on the ground as it's overlapping and underlapping, all that kind of stuff, the earth shakes and it rattles. Well, depending on how far you feel it, the intensity, like the height of the movement of the ground, 100 kilometers away, for example, will measure the intensity of that earthquake. So when you hear in the news that there's an earthquake of magnitude 5.5 versus one of 7.2, or an earthquake of 2.1 versus a 9.1, we know that a 2.5 earthquake, magnitude earthquake, is less intense than a 5.7 magnitude earthquake, because obviously the numbers are bigger. 2.5 versus 5.5, well, 5.5 is larger, so you know it's going to be a bigger earthquake, but how much bigger is it, right? So what Richter did here is he did basically what we did here as an example. He took this number, like 100,000, and say, let's talk about 10 million. To quantify this earthquakes, he converted these logs, by using the log, he converted these exponential numbers, these large numbers, like 100,000. Earlier we said that we take 100,000. It's the same thing as 10 to the 5th. By taking the log of this number, we're able to take this and convert it down to the base. So the log base 10 of 100,000 equals to 5. So here, for example, we would have like an earthquake of magnitude 5. And then over here, let's say that we have one with a 10 million. Now we have 10 million, so a lot more circles. It's the same thing as saying 10 to the 7th power. by taking the log of both sides, we're able to take this and put it down here. So now we have log base 10 of 10,000, or 10, a lot of 10,000s, 10 million equals to 7. So an earthquake of magnitude 5 versus magnitude 7, yes, they're 2 units apart, but they're way more intensified and way more of magnitude. The magnitude increases by 2, but the intensity increases by 100, right? 100,000 times 100, if you add 3 more zeros, let's see, 1, 2, all right, if we add 2 more zeros, if we multiply this by 100, we're saying that an earthquake of magnitude 5 versus an earthquake of magnitude 7 is 100 times more intense than an earthquake of magnitude 5. So 5 and 7 are close to each other, which is the property of logs. It allows us to minimize these numbers, but they're really so far apart. An earthquake of 5 versus a 7, you're talking about 100 times different intensity. And this is why there's so many deaths attached with earthquakes in different parts of the world. California, there's different places where the plate tectonics is part of your geographical boundaries. So you're going to experience earthquakes a lot because of the shifts that are constantly happening. Now, sometimes when an earthquake is so small, you don't even register it, right? You don't even feel it in some locations. So they don't even talk about an earthquake of magnitude 1 versus some that are higher than 4 or 5 and even up to 8 and 9. Anyway, hopefully this sort of gives you an idea of how earthquakes can be, you can talk about how the magnitude, by using this Richter scale, how you can lower the magnitude to smaller numbers, but still looking at how much more intense it is. We're going to be talking about how to convert back and forth as we're doing here, these numbers, exponents to logs and logs to exponents. But I wanted to give you this as a background to help you maybe understand why it is that we're doing that. We've been dealing with exponents so far, with fractions as exponents. We're talking about how to solve those equations, those kinds of things. Now we're going to say, well, how do we use this other equation, introduce it so that we can talk about smaller numbers versus these really large numbers that are so far apart. I hope that makes sense. If it doesn't, look up a little bit on the Richter scale, look up on earthquakes. You can read up more about this stuff, or you can talk to me and we can chat more about the specifics of this kind of stuff. So, as I mentioned earlier, the exponential function that we just spoke about, right, it's this function, the exponential function, is actually the inverse of the logarithmic function. So this is the log function. This is what it's going to look like. We spoke about in the last video, in the last unit, that when you can reflect a function across the y equals x, when it's reflected over, if it's reflected over, then they are inverse of each other. So they behave inversely to each other. As one number increases exponentially, one of them decreases. And that's why we're dealing with small numbers when we're dealing with really large numbers. This 10 to the 7th power comes down to just 7. Right? These large numbers become smaller numbers. Now, these are the two most basic types of logs or exponentials that we deal with. 10 to the x, where 10 is the base, and e to the x, where e is the base. The log is this one. So whenever we have the inverse of 10 to the x, the log is going to be a base 10. Technically, there is supposed to be a 10 right here as the base. So log base 10 of x. But we don't put the 10 because it is implied. It's so common. Whenever you don't see the 10 in there, it is common and it is assumed, right, that it is going to be a base 10 because it's the inverse of the most common type of log, or the most common type of exponent. 10 to the 5th power, the inverse would be log base 10. So adding a 10 or not adding a 10 doesn't really matter when it's 10 as the base. The other type of common exponent that we deal with is e to the x. So when you take the log of base e, we call this the natural log. So these two logs are the same. You can refer to a log base e or natural log, and we're talking about the same type of log. The reason why it's called natural log is because you use this type of growth, exponential growth, in nature a lot. So anything that measures exponential growth, like bacteria production, viruses, like this pandemic that we're going through, right? It grows exponentially in a natural form, not in a machine calculated form. So when it grows in a natural form, these viruses are spreading. You don't have control on how often it spreads. It spreads on its own at a specific type of rate. And that rate is this E constant that we're dealing with. Anyway, these are the two main types of functions, 10 to the x and e to the x. And the two most common bases are 10 and e for natural log. So you can actually express it in more than those two bases, right? We can talk about 2 to the fourth being 16. We can talk about where 2 is your base. We can say 4 cubed is 64. We can say 3 squared is 9, right? Clearly, here we have 2, 4, 3. They're all different bases of this exponential function. So you could take different logs. You can have a log of base 2. You can have a log of base 4. And you can have a log of base 3. You can really have logs of any number you want. Decimals, pi, fractions. You can have bases for anything that you really want. So we're going to use these two as the most common ones, but I'm going to expose you to different types of logs with different bases. And really, this is the reason why we're dealing with converting exponentials to logs and logs to exponentials, so that no matter what type of base you're dealing with, we can convert from one to the other naturally. And like here, we would say log base 2 of 4 is 16. So we're going to be able to convert back and forth comfortably between these kinds of equations. I hope this is making sense as we progress. It'll make sense once we start doing some problems. I'm just trying to give you some background of how this works and why this works. So here I'm going to show you real quick on how to convert a log function to an exponential, right? Here we have just as a quick background, we're going to have the log. We're going to have a base. We're going to be denoting it as the letter B for base of some sort of variable or number on the inside, and it's going to equal to something else. So here we're going to be dealing with different values, but this is the base. Log base B of something equals something else. So here we have log base 2 of 8 equals 3. So you can put parentheses around the 8. It just says that this log function is a base 2. So how do we convert it? Well, what we do is we take that base and we're actually going to move it to the other side. We're going to use this base and push that 3 up. So now by moving the 2 over, 2 to the third power, the 3 goes up as an exponent, and on the left hand side, the log disappears. So 8 is the same thing as saying 2 to the third, right? 2 times 2 times 2 is 8. And that's how we connect these two. You can disappear this log by moving the 2 over, raising the number on the right as the exponent, and it goes from log to exponent. Let's try another one. Let's take this 5, push it up. We have 5 to the second power equals x, and this log disappears. We do the same thing over here, but now see how it's a little bit reflected. We can move this 2 to the other side. So 2 to the y equals x. This log disappears. Over here, we would take this x value, push it over. We have x squared equals 100. Now, right now, all we're doing is converting from log to exponents, and then a little bit from exponents to logs, back and forth. Later, we'll talk about how do you solve these equations and why are they useful? Why would I want to convert from log to exponents or exponents to logs? And that'll come in here in a couple more videos, probably next week actually, or the week after. All right, so basically as a quick recap, to convert the log, base, say b of y equals x, we're going to take the base, push this value up, and leave the y by itself equals b to the x power. This is how you convert it using the definition. Now let's go backwards. If we start with the exponent, how do we introduce a log to bring things down? Okay, so now we're going to reverse the order. Instead of pushing the number up, we're going to bring this number down with us. Okay, and here's where it's called like the lasso method, right? We're going to take this number and say we start here. We're going to take the base. This here is part of the base. This is going to be wrapped downward, right? This 5 is going to drop. And then we're going to take the log of 32. And this 2 that came down becomes the base. So the log base 2 of 32 equals 5. We're going to take that base of the exponent and bring it down. We're going to bring it down to the bottom as the log. And we're introducing the log here. Same thing here. We start with this 3 as our base. The 3 is going to become the base of the log. And it's going to go to the right-hand side. So we're going to take the log of 27. And we're going to take this 3 and bring it down. So log base 3 of 27 equals x. Let's try it as well over here. We're going to take this 7. We're going to take the 7 and bring it back down. So we have the log base 7 of y equals x. Some people call this a lasso method because you're sort of lassoing the 7, the base, and you're pulling it down towards you, right? It's kind of like taking a rope and launching for that 3 as a base and then pulling it back down and bringing it to you, down to the log. So let's take the log of 64 and lasso that 4 down as a base. That'll equal the exponent just comes down as your 3. Now, if converting from logs to exponents makes more sense to you, if you feel that it's easier to visualize the 4 pushing the 3 up, right, then do that. Convert your log that you found back to exponential. See if you got it. So move the 4 over. It puts it as 4 to the 3rd power equals to 64. And the log disappears as a way to sort of check that you did it correctly. Some people prefer to do exponentials as logs. Some people prefer the other way around. Whatever works, we're trying to get comfortable doing it both directions, right? So quick recap. We have log of some sort of, the exponential. We have the base to some power, right? Some value equals y. This is our basic exponential equation. We're going to lasso this b, bring it down. So x equals the log base b of y. And this is how these two equations are connected. All right, let's do an example here where we now evaluate logs. Basically, evaluating a log is tell you now there's no variables, right? Notice how in none of these examples there are no variables. And what we want to do is we want to find what are the values of these 4 different logs. What do they mean? What does it mean to have log base 5 of 25? What does that number equate to? So we're going to evaluate these 4 examples and show you what they mean. So this equals something really, right? Question mark. They all equal something. We want to know what is the representation of this log so that we can understand what it means in terms of a number that we're used to. It's hard to understand what log base 5 of 25 means, but if I tell you it's this number instead, then it can make sense in your head. Okay, these 2 are equivalent. They're just written in different forms. So if we were to convert this to exponential, this 5 would push this question mark up to the top, and the log would disappear. So this is the same thing as saying 25 equals 5 to the question mark. So 5 to what power equals 25? The answer is 2. 5 squared is 25. So instead of saying log base 5 of 25, you can also just say 2. This equals 2. Log of 10,000. Now, if you remember back to a few slides ago, we said that when there's no base, that there's assumed to be a 10 down there because it's the most common type of log, right? This one has the log base 10 as well, right? If it doesn't have a base, it's assumed to be 10. If it's natural log, then you can convert this natural log, right? If we have a natural log, you can convert this, say natural log of x, you can convert it to saying log base e of x. Those two are the same. Now, you'll see that in your homework assignment, but this one doesn't have a base, but because it's natural, it's assumed to be e. This one, on the other hand, doesn't have a base, but because it's a regular log, we assume that it's 10. I hope that's not too confusing. So, let's go ahead and convert these last three, and we can call it a day. So, we take this 10, we push that question mark up, the log disappears. So we have 10,000 equals 10 to what power? Right? So notice how there's 4 zeros? That means it's 10 to the 4th power. So this represents 4. This question mark equals 4. So you can say, instead of dealing with log base 10 of 10,000, you can just say, hey, let's just talk about 4. Right? Here's where the power of logs come into play. Instead of dealing with numbers so large in the 10,000s, you can just say, hey, it's 4, or hey, it's 2, right? Let's do an example where we're dealing with a fraction here. It's 1 over 81. Let's take this 9, move it over, the log disappears, so we have 1 over 81 equals 9 to the what power? Now, you might have to remember a little bit to a few videos back when we dealt with exponents or rules of exponents, but positive exponents deal with whole numbers, right? Negative exponents deals with those fractions. So technically, 9 to the 2nd power equals 81. But since we're dealing with a fraction of 1 over 81, this is where we put it as a negative 2. 9 to the negative 2 flips this 81 upside down. That's 1 over 81. So, log base 9 of 1 over 81 is negative 2. Let's try this last example. Log base 10 of 10 equals something. So we lasso this up, push that 10 up, the log disappears, 10 equals 10 to what power? So 10 to what power equals 10? 1. Whenever the base and the number are the same, I'll erase this a little bit so you can see it better. Whenever the base matches it, it'll always be 1. See how this base 10 and 10 are the same? Whenever they're equal, it'll always be 1. Always. So, say we have log base 5 of 5 equals something, right? If we move this 5 over, the log disappears. 5 equals 5 to what power? 5 to the 1 power will always equal 5. So whenever these match up, your answer will always be 1. Alright guys, I hope this helps. You might have to pause this and rewind a little bit and try a few examples on your own, but all this first video is converting from one format to another. Can you take an exponential number and convert it to a log? And can you go from logs to convert it to exponential? And the purpose of all of this, of going back and forth right now, is you can take these large numbers, like 10,000 or 100 million or 1 or 10 billion, and convert it to a smaller number like 4. So it's more quantifiable and within grasp and more understandable, right? Let me know if you need any help. Please, I know this stuff can get a little complicated and tricky, especially as we're talking about logs and something that you've never spoken about before. But we'll do this together, and just let me know how I can help. All right, calculator.